Hello everyone, and thanks for joining this session on Consul. As the title shows, I'm going to be talking today about service discovery with Consul on Kubernetes, as well as go into what Consul has to offer on the service mesh front with Connect. I'm going to spend the first half of the session talking through these topics of service discovery and service mesh and how it ties into Kubernetes. And I want to flip over after to a demo, and I'll show you how Consul is being used in my Kubernetes cluster. So let's get right into it, and I want to start off by quickly showing this slide and level sliding on these terms before diving deeper into the content. If you've looked into Consul on your own already, whether it's through the HashiCorp website or watch a couple past talks, you've likely seen a diagram similar to this. And I think this diagram shows a brief overview of where we've been in the past with bare metal and virtual machines, and then moving over to containers. I think in order to understand how these concepts work, we need to look into why we need them. On the left, we see an older or traditional way of deploying applications, whether it is directly on bare metal machines or using some sort of hypervisor like VMware. With a lot of customers that I work with today, it is still the norm to deploy applications on servers, whether they are virtual or physical, and then those get a fixed IP. Firewall rules are then put into place based on that IP and can take weeks to implement just to get two services to talk to each other. As we shift to a more dynamic deployment model, as shown on the right with containers, we no longer can depend on a service having a particular IP address. Schedulers such as Kubernetes or Nomad can deploy and destroy services at any time for situations like node scale up and node scale down. Due to this dynamic nature, we need an efficient alternative to reference these services, and on top of that, have the ability to control and monitor the communication between them. With that comes in the idea of service discovery and service mesh, where we now focus on registering these new dynamic services to a central service registry and let that become our single source of truth. Once we have the discovery piece nailed down, we can move on to the mesh side of things, again, which allows us to monitor communication between our services and control that communication as well. These topics are the ones that I want to dive into today and demonstrate how they can all tie into Kubernetes. So before we get into things any further, I want to quickly introduce myself. My name is Mammoliti, and I'm a consultant out of Toronto, Canada, working at Arctic. My day-to-day is mostly focused on working with customers to enable them with HashiCorp tooling, specifically around Terraform, Vault, and Consul. On top of this, I spend a lot of time in the microservices space with customers as well, working on all things Kubernetes and helping them migrate to a more containerized approach. You can find me on Twitter and GitHub with that handle below my name. And the code I'm using in the demo coming up shortly will be available on my GitHub as well. So we talked high level on what service discovery is, and now I want to dive into it a bit more, and more specifically Consul's approach to it. When we talk service discovery, what we really mean is how can I find instances of service A? I no longer want to have to worry about connecting to a fixed IP, but rather reference a service by name and let a tool like Consul handle the destination instance for me. In a containerized environment, the ideology becomes extremely important because the IPs that are assigned to an instance of a service are meant to be ephemeral. So how does Consul do this? And how can we shift from hard coding IP addresses and achieve a more dynamic setup? Consul keeps a centralized service registry that stores the location information such as IP address for Consul-enabled services, and it does this by running a local sidecar agent on each node in the environment. The Consul client agent is responsible for registering new services that come up on the node to the service registry, and also provide consistent health checks to ensure that we don't direct traffic to an unhealthy instance. So with that, looking at the diagram on the right, I should be able to delete one of the app A pods, assuming we're in Kubernetes and app A is a deployment, and Kubernetes will spin up a new pod with a new IP that the Consul client agent will register back to the service registry. And all this is done automatically, and at the end of the day, that service endpoint still remains the same. In the diagram, you'll also notice that I highlighted the Consul client agent, and the Consul client agents also expose an HTTP and DNS API so that services can reference it locally in an attempt to help discover and communicate other Consul-enabled services. Now that we've talked about the service discovery piece and Consul's approach to it, I want to dive into service mesh and how that is provided with Connect, which is Consul's service mesh feature. When we talk about service mesh, what we're essentially talking about is an infrastructure layer which sits above the network and below the application. This in-between sort of layer paves the path to provide features such as service-to-service authentication, encryption using MTLS across the mesh, and observability into traffic patterns. So how does it do this? Well, Consul uses the concept of a proxy that is co-located with the application. So in the instances of Kubernetes, it is running in the same pod. The benefit with this separation of duties is that they are not dependent on each other. So ops teams can come in and make changes to the proxy. Maybe they want to make a version update without having to get the development team to rebuild the application. So spanning off of service mesh in general, and now let's talk about how Connect enables it specifically. So the first point that I like to discuss is intentions, and intentions in Consul provide us a way to define which services can talk to which. Now this is very similar to anyone who's worked with Kubernetes network policy, where we can essentially define the same thing. But again, we're looking for visibility and control at the mesh level and provide a single pane of glass to control all of these features. When handing these types of things over to Consul, we're no longer locked into intentions at the Kubernetes level. We can expand the mesh to virtual machines and enforce the same policies all the same way. And again, this is all managed by Consul. Customers that I work with are never really on Kubernetes if they're trying to migrate to a more containerized approach. They often have a lot of applications still running on virtual machines. So something like this where I can expand a mesh to containerized applications and non-containerized applications really appeals to them. Second thing is communication over mutual TLS, and this is often thrown in the conversation when service mesh is brought up. What this allows is the ability to enforce that any services that communicate are doing so in a secure way. The final point is observability into the mesh, and I've hinted on this throughout the previous slides. When using Consul and Connect as your mesh, we get a consistent way to observe stuff like traffic patterns, latency, or error rates, and all this is done without having to ensure a development team has baked that sort of stuff into their application. This goes back to that separation of duties that becomes a real thing with a co-located sidecar proxy. I've also added a diagram on the right showing an example dig command, which is querying Consul to discover any services of my app. When we get into the demo in a few minutes, we'll go through the same sort of exercise. So tying this all together with Kubernetes, and since this talk is about Consul on Kubernetes, I want to talk a bit more about how HashiCorp has gotten Consul to fit so well in the ecosystem, and then go over a high-level architecture diagram. So it's important to know that Consul offers first-class support with Kubernetes by making it super simple to adopt Consul into the environment. The first point here that I want to highlight is the ease of installation of Consul through the Helm chart. The Helm chart provides a simple way to deploy Consul in quick and repeatable fashion, and because it is a Helm chart, it can be even easier to deploy Consul through something like Terraform or a CD application like Argo CD. Consul also has the ability to sync Kubernetes native services into its own registry, which essentially gives us the ability to expand the service discovery scope and help connect more applications. We also have the ability to sync services outside of Kubernetes as well, and still manage it through that single pane of glass. Remember, earlier I mentioned in most situations, not everything is containerized. Applications are still going to be running on virtual or physical machines that need attention as well. Another feature that comes with Consul and Kubernetes is the idea of auto-injection, where we can tell our Consul deployment to auto-inject every namespace besides kubesystem, which means anytime a pod comes up in this namespace, it automatically gets injected with a sidecar proxy. Of course, this auto-injection can be fine-tuned to specific namespaces and can also be controlled at the pod level or something at a higher level, such as a deployment, stateful set, or stateful set. And finally, one of the big benefits with Consul as a service discovery and mesh tool is the ability to extend your mesh across multiple clusters. Customers, again, that I'm working with that are now starting to adopt a containerized approach with Kubernetes are deploying more than one Kubernetes cluster. So something, again, that also really appeals to them is be able to have multiple Kubernetes clusters deployed, but span that mesh across both clusters or multiple clusters and be able to use the same Consul service discovery registry and Consul service mesh. And this can be done with something like a mesh gateway. So building off of the last slide and focusing on just one cluster for now, this is a high-level architecture overview of Consul deployed in a 3-node Kubernetes cluster. Consul server is deployed as a stateful set, and in this architecture is deployed with 3 nodes. In general, your Consul server should be about 3 to 5 nodes for high availability and satisfy the RAF consensus algorithm. These server agents follow a leader-follower model and hold that state of your Consul cluster and contents such as the service registry. Underneath that, we have the console client agents, which we talked about a lot previously, and those agents are deployed as a daemon set, which is a type of Kubernetes deployment, ensuring that each node runs a copy of the pod. And this makes sense because the agents are responsible for registering services that come up on the machine that it is running on. Looking on the right, we see another 2 pods deployed with our applications. You see that each application pod has an Envoy sidecar proxy deployed beside it, and again, these are responsible for enforcing anything from intentions or enforcing mutual TLS between app A and B. No traffic is actually happening between the 2 applications directly. All communications go through the proxies, which again gives us full insight to that traffic at the console level. So now let's get into the demo. I have a GKE environment up and running, and now we're going to use that to deploy our console environment. After that, I'm going to deploy my application, and then we'll start to demonstrate how to query the console service registry, and then start looking at how we can basically set up and block communication and allow communication with console intentions. Okay, so let's get into the live demo. I'm going to show off that I have my 3-node GKE cluster running, and I've already created the console namespace here, so we can do a get namespace to show console already exists. And now what we can do is just verify that there's nothing in that namespace. We see console is now empty, so we can go ahead and create the application. So we can show off my values.yaml, and in here the things to look for is that we have connect inject enabled true, but it's denied by default, so we have to add that through annotations in our deployment. So let's go ahead and clear this, and what we're going to go ahead and do now is template out using Helm our Kubernetes deployment. What Helm template does is it basically writes out all of the Kubernetes YAML for you into standard out. So what we'll do is then we're going to pipe it to kubectl apply, which is going to go ahead and deploy console for us in our Kubernetes cluster. So we'll give that a few seconds, and we should see everything get deployed. We can now see stuff like service accounts, config maps, and everything else related to console is now getting deployed in our console namespace. So it looks like everything got created successfully. So what we can go ahead and do now is we'll go ahead and clear this, and what we want to do is just do a watch on the get pods for console to make sure that everything comes up. So what this watch will do is it'll refresh every 2 seconds, and we'll just wait for all of our server agents and client agents to come up successfully. So what we're going to look for here is our server agents will come up first, and then followed by that will be the top 3 pods there, which are our clients. It usually takes about 40 seconds to complete end-to-end, so it's pretty quick. And deploying console, like I mentioned earlier, is super straightforward to do in Kubernetes. So we see our servers come up, and now we're going to deploy, and now we're going to wait for our clients to come up as well. So we see the first one's done, the second one, and the third one should be done. It's done now as well. Awesome. So we can go ahead and get out of this. And what we want to do is we want to get the IP address of the console DNS server, which will be a cluster IP in our Kubernetes cluster. And the reason why we want to do this is because we want to basically set up a rule in our cluster saying that anytime someone tries to query a service that ends in .console is to redirect to that console DNS instead of using the kubedns that comes with Kubernetes. So we're going to go ahead and get the output of a get service on the console DNS. And what we should get back is our internal IP. And this is, again, the internal IP address of our console DNS server. So we can now edit a config map, which I've already pre-populated. So we'll open that up, and we're going to replace the IP address that we have here with our new DNS IP. And again, we're creating a stub domain here that anything that ends in .console to forward that to anything that ends in .console to this DNS server. Okay, that's awesome. So now that we have that done, we can go ahead and apply this config map. And those changes will make those changes right away. So let's go ahead and clear this now. And what I want to do is look at our application that we're going to deploy. So to keep things clear, we're going to create a Pokedex, which is a Golang application that I made that queries the Pokemon API. We're going to create a namespace to keep things clean. And this is a standard Kubernetes deployment, but what I want to make note of is the annotation where we have connect inject true, which means that any pod that gets deployed from this deployment will get a sidecar proxy attached to it. In the next page here, we have just a standard Kubernetes service, but the other thing to pay attention to is the pod that we're deploying next to it. So what this is going to be our client pod that also has a connect inject true, so it's going to get a sidecar proxy as well, but it also has a service upstream of Pokedex on 8080, which means that this client is responsible to talk to Pokedex on port 8080, so it's going to bind that port to localhost on this client pod. And we'll see that in a second when we go through the actual service mesh piece of the demo. Okay, that's great. So now we can go ahead and clear this, and we're going to go ahead and deploy our application in our Kubernetes cluster. And once that's deployed, we can now go ahead and take a look in that namespace to verify that the pods have come up successfully. And it looks like they have. All 3 of 3 are running. And again, now this is just responsible for the actual application itself, and in that pod exists the sidecar proxy container as well. So now that we have everything set up, let's go ahead and look at a sample dig command. So what we want to do is we want to query the Consul service registry. So what we're going to do is we're going to run a Kubernetes job that's responsible for digging against this service here. And what we should get back from this is the IP address of the of the service pod that we've just deployed. So now we can do this, we can apply our job, and what that's going to do is it's going to spin up a pod, and those pods logs will show us the output of the dig command. So we can see it already completed. We can go ahead and clear this. Let's get the ID again of that job that just ran. We can copy that out, and we can do kubectl logs on that pod, and we're going to get the output of the dig command that the pod would have ran. And in the answer section specifically, we see the IP address of the pod of our service. So let's try something else, and let's test Consul a bit here. What we're going to do is we're going to up the replica count of our deployment. Instead of 1 pod, it's going to now be 3. So we edit the deployment and go to the replicas, and instead of 1, we'll up it to 3. And what this is going to go ahead and do is deploy 2 additional pods of our application. So do a kubectl get pods, and now we should see those 2 additional ones. And they've all come up running, and they also have the sidecar proxy injected into them as well. So now let's go ahead and delete that Kubernetes job that ran the dig command, because what we're going to do is we're going to run it again, and what we should get back in the answer section is now 3 IPs. So we're going to apply the dig job, and we can do a get pods to get the new ID of that job. And then we can do a kubectl logs on that pod, and in the logs we should now see that we have 3 IPs in the answer section, which we do, perfect. So now anytime we try to query that, we get back 3 instances of our application. So now let's work on the service mesh side of things. So the first thing we want to do is we want to go ahead and get the public IP of our Consul UI. So because the service is a load balancer type, GKE is going to expose a public IP that we can copy and we can access from outside of the cluster. So we can go ahead here, and then we hit with the Consul UI. So in the Consul UI, the first thing you hit when you upload it is you're going to get a list of all the services that Consul is aware of. So we get the Consul service itself, we get our Pokedex service along with a sidecar proxy, and we also get our static client. So because everything is injected with the sidecar proxy here, that's why we see it in the list for Consul. There's other stuff here like Arctic, so we could see that's our data center name. We can see the nodes here of the nodes that are actually running Consul for us. And then you can see other stuff here like key values and ACLs. But we want to focus on right now for service mesh is intentions. So let's go ahead and create an intention. And the first intention I want to create is a deny all. So what this is going to mean that no services can talk to each other over the Consul service mesh. We choose the source to be star for both source and destination. We choose deny, and then we're just going to add a description here, basically again saying that all communication between the services on the Consul mesh are denied. We can go ahead and click save, and we're going to flip back over to the terminal. And now we're going to run an exec, which is a kubectl exec as if we're running a command in that pod. So we're going to choose the static client because that's the one that can essentially talk to our Pokedex service. So we're going to exec into that, and what we're going to do is we're going to do a curl command, and we're going to curl it locally because I remember I said with the upstream, we're binding the 8080 port locally to the static client. And now we're going to hit the endpoint of our Pokedex service. I'm going to choose Charmander to get information on. And what we get back should be an exit code 52, which basically means that the curl was blocked and essentially that traffic was blocked. because of our deny rule. So now let's go ahead and add a allow rule. So we're going to choose our static client as the source, Pokedex as our destination. We're now going to click allow, and in the description we're basically going to say that static client is allowed to talk to Pokedex. So with this intention in there, or these two in there, all we're allowing is this is the only two communications that we're allowing over the mesh. We can see now that it's been added on top, it has a higher precedence because it's an allow. And we can also filter by allows, denies, and you can also see on the right that we can search intentions if we ever got a lot more than just the two that we have. So we're going to flip back over to the terminal. We can run the exact same thing again, but because I'm feeling a bit more confident this is going to work now, we can pipe this out to JQ to output the JSON to make it look a bit more pretty. So I hope this gave you a brief introduction of service discovery and service mesh with Consul and Kubernetes. Thank you for tuning into this session today, and if you have any questions, please let me know below, and feel free to reach out, whether it's on GitHub, my Twitter, or by email as well. Thank you.